Alright, what's up guys? So I am here to teach you about torque. So let's start off with the little symbol. The little symbol for torque is a T with a little squiggly on the top. That sort of looks like a backwards J. And now, more importantly, here's the equation for torque. It's torque is equal to F times D times sine theta. F standing for force being applied, D standing for the distance of the force being applied, and theta standing for the angle of the force being applied. Okay, since torque usually deals with circular objects, you can replace the D, distance, in the equation with R, radius. So you do F times R times sine theta. And one last thing is that the units for force are newtons, and the units for radius are meters. So F times R, which is what torque is equal to newtons times meters. So newtons meters are the units of torque. Alright, bear with me and think that this arrow I just drew is perfectly straight up, that it's perfect, right? What do you think the angle of this arrow is? Okay, if you haven't gotten it yet, it is 90 degrees. So that means in your torque equation, you would plug in sine 90. Now, if you were to grab your calculator and plug in sine of 90, you would get that the calculator says that it is, okay, no, I'm sorry, that was not English. If you plug in sine 90 in your calculator, you will get the answer is 1. But make sure that your calculator is in degree mode, and you will get that your answer is 1. This means that F times R times sine 90 is the same thing as F times R times 1. Now, when sine is 90, you begin dealing with components, with the x and y components, because when sine is 90, that means that the force has an x component and not a y component, or that it has a y component and not an x component. That means that if the force has an x component, the radius has a y component and not an x component. And it works the same way around. If the force has only a y component, then the radius has only an x component. This only works when the degree is 90 degrees. So you have your R and your F right there, your radius and your force. So which do you think represents the y component and which represents the x component? Give it some thought. The F has the y component. That automatically means that the R has the x component. So torque in this case would be F times R times sine 90, which leads to Fy times Rx. Yeah, sorry about that. Okay, there you go. Now, in this case, the box has a force being applied to it that is perfectly horizontal. It is perpendicular, by the way. I know it's poorly drawn, but bear with me. So, in this case, what do you think would be the x component and the y component? Give it some thought. Okay, if you don't get it, you can just pause. The F would be the x, and the R would be the y. So this means Sorry about that. So this means that in this case, torque is equal to F times R times sine 90, which in this case is Fx times Ry. So to sum it all up, it's all about the x and y components when theta is equal to 90 degrees. Okay, let's see if you get this. So, read the problem. The drawing to the right shows an overhead view of a horizontal bar that is free to rotate about an axis perpendicular to the page. Two forces act on the bar and they have the same magnitude. However, one force is perpendicular to the bar and the other force makes an angle theta with respect to it. That means that the force that is perpendicular to the bar, the angle is 90 degrees. The angle theta can be 90 degrees, 45 degrees, or 0 degrees. That's for the F that's slanted. Rank the values of theta according to the magnitude of the net torque that the two forces produce, putting the largest net torque first. Okay, so first thing you have to do is just draw it out. Even if you have the drawing there, just draw it out, because I don't know if it'll help you, but it just helps me to see it in my mind. Okay, the next thing you want to do is write down the equation of net torque. Net torque is also equal to all the torques added together, just torque 1 plus torque 2. So, let's say that torque 1 is equal to the force that's slanted, and we don't know what the theta is, and that torque 2 is equal to the perpendicular force, where we know that sine is 90. So honestly, we don't need to worry about the second torque in this problem. We just need to look at the first torque where we don't know what the theta are. So let's write down the three possible degrees they gave us. They gave us sine 90, sine 45, and sine 0. First thing you want to do is plug these into your calculator when it is in degree mode and see what values it gives you. Once you do that, you get that sine 90 is 1, sine 45 is 0.707, and that sine 0 is 0. Okay, so now just plug those numbers into the torque equation, and let's start off by using sine 90. If you multiply anything by 1, it's unchanged. It's not getting bigger, it's not getting smaller. So sine 90 usually gives a pretty big torque. And then if you plug in sine 45, which is 0.707, anything multiplied by 0.707 is going to be smaller than the original value. So you know sine 45 is going to be smaller than sine 90. And then when you plug in sine 0, you get 0. So anytime you multiply anything by 0, the result is 0. So by that logic, the biggest torque produced is by sine 90, then by sine 45, and then by sine 0. Alright, number 2. Sometimes, even with a wrench, one cannot loosen a nut that is frozen tightly to a bolt. It is often possible to loosen the nut by slipping one end of a long pipe over the wrench handle and pushing at the other end of the pipe. With the end of the pipe, does the applied force produce a smaller torque, a greater torque, or the same torque on the nut? So write down your torque equation, which is FR sine theta. Let's just eradicate the sine theta here because it's not important. So you get torque is equal to F times R. So F and R are directly proportional to the T variable. This means that if one gets bigger, the other gets bigger as well. So if you have a pipe or a wrench and you make it longer and you apply the force from a greater distance, making R a bigger number, that means that your torque is going to be bigger. So if R is big, torque is big. If R is small, torque is small. So if the wrench got bigger, which the wrench represents the radius, that means that the torque got, the answer is bigger. Alright, number 3. Is it possible for a large force to produce a small or even zero torque? Okay, so let's say that your force here is 100,000 newtons and that your radius is 0.000000001 meters. You know that your torque is F times R. If you multiply those two values, you get 0.001 Newton meters. So yes, it is possible to have a massive a massive force and a small torque. That can only happen if your radius is small though. Another way where you can have a large force and a small torque is if you have a small degree. So let's say your force is 100,000 newtons, and your radius is 100,000 meters. But your degree is 0. We know from my previous lesson that sine 0 is just 0. So if you do F times R times sine 0, you get 100,000 times 100,000 times 0, and that just produces a 0 torque. So those are the two ways where a massive force can produce a small torque. Now part B asks, is it possible for a small force to produce a large torque? And the answer will come up shortly. Let's say that your F1 is 0.00001 newtons, but your radius is 100 million meters. Well, torque is equal to F times R, so if you multiply those two odd values, by odd I mean weird, by the way, I don't mean like odd or even, you get that it's 1,000 Newton meters. So it is possible for a small force to produce a large torque. Okay, yeah, sorry about that rough transition. I'm not really good with this app and I messed up a couple times. But bear with me. Alright, let's deal with the next problem. The wheel of a car has a radius of 0.35 meters. The engine of the car applies a torque of 295 Newton meters to this wheel, which does not slip against the road surface. Since the wheel does not slip, the road must be applying a force of static friction to the wheel that produces a counter torque. Moreover, the car has a constant velocity, so this counter torque balances the applied torque. What is the magnitude of the static frictional force? Okay, that problem seems mind-blowing, okay? But it's not. First thing you want to do is write down all the values you have. So you know that your radius is 0.35 meters and you know that your torque is 295 Newton meters. Okay, the question asks you for the force. You know that T is equal to F times R. They give you T and R and they ask for F. This is just basic algebra now. Plug in the values and divide 295 by 0.35 and you'll end up getting 842.86 Newton meters. Sorry about the rough transition again. I'll go back. Okay, if you haven't written it down, just pause. I'm gonna move on. Alright, so you are installing a new spark plug in your car and the manual specifies that it be tied into a torque that has a magnitude of 45 Newton meters. Using the data in the drawing, determine the magnitude F of the force that you must exert on the wrench. Alright, first things first, if you have no idea what you just read, write down the values they give you. Torque is equal to 45 Newton meters. Torque is also equal to F times r times sine theta. They give you that theta and they also give you that r. And they ask you for the force. So this is just like the problem from before. Just plug in the values. 45 is equal to F times 0.38 times sine 50. Okay, sorry about that. I rewrote everything. It's 45 is equal to 0.28 times sine 50, which in the end gives you 209.8 newtons. Sorry about that again. Like I said before, I'm not that great with this app. Alright, let's move on. Alright, so two children hang by their hands from the same tree branch. The branch is straight and grows up from the tree trunk at an angle of 27 degrees above the horizontal. One child with a mass of 45 kilograms is hanging 1.3 meters along the branch from the tree trunk. The other child with a mass of 35 kilograms is hanging 2.1 meters from the tree trunk. What is the magnitude of the net torque exerted on the branch by the children? Assume that the axis is located where the branch joins the tree trunk and is perpendicular to the plane formed by the branch and the trunk. Okay, this might seem crazy, but like the other problems I said before, write down what you know. Here, just draw what you think is happening. So I'm drawing up this little tree. I'm gonna make it colorful. I'm gonna add those leaves, not the branches, and that's the branch you want to worry about. Alright, I know no tree exists like that, but for the sake of the problem, bear with me. So, here you have your first kid. Here you have your second kid. There you have your degree, which is 27 degrees. Then the distance between the end of the branch and the first kid is 1.3 meters. Then the distance from the end of the tree and the second kid is 2.1 meters. The first kid is 44 kilograms and the second kid is 35 kilograms. To get the force that they apply, you just multiply by 9.81 to get their weight. And once you do that, you get 431.64 newtons for the first kid and 343.35 newtons for the second kid. Alright, so I hope this helps out a little bit. Now let's solve the problem. They ask you for the net torque. That means that you have to find the torque of each child and then just add them up together. So let's say torque 1 is equal to the first kid, which is 44 kilogram boy, and torque 2 is the 35 kilogram boy. I'm gonna make this neat so it's easy for you to understand. So torque 1 is F times R times sine theta. Torque 1 is equal to 431.64 newtons times 1.3 meters times sine 27. That's because the first boy, the force that he applies is that 431.64. The distance that he is from the axis of rotation of the tree is 1.3 meters, and the degree, which they tell you, is 27. Plug that into your calculator and you get 254.75 Newton meters. Now do the exact same process for torque 2. Do F2, which is equal to 343.35 newtons, multiplied by 2.1 meters, multiplied by sine 27. I know that says sine 50, but I'll fix it in a second. There you go. Once you plug that in, you get 327.34 Newton meters. Now, net torque is torque 1 plus torque 2. So then you just add those two big numbers and your torque is 582.1 Newton meters. Sorry about that transition again. There you go. That's the answer. Alright. Okay, let's carry on. So this drawing shows a jet engine suspended beneath the wing of an airplane. The weight W of the engine is 10,200 newtons and acts as shown in the drawing. In flight, the engine produces a thrust T of 62,200 newtons that is parallel to the ground. The rotational axis in the drawing is perpendicular to the plane of the paper. With respect to this axis, find the magnitude of the torque due to the weight and to the thrust. Okay, so write down what you know. That is the first step. Okay, sorry about that. Oh my god, give me a second. Okay, there you go. So the weight here is negative 10,200 newtons because look at W, it's pointing down, okay? And the T is negative 62,300 newtons because look at the arrow, it's pointing towards the left. Anything pointing down and towards the left means that it's negative. Alright, they also give you a degree sign. So draw it out to make it easier, and they give you the distance. So find your x and y components here. So cos of 32 is equal to y over 2.5 because cos is adjacent over hypotenuse and the adjacent one is y. So y is equal to 2.5 cos 32. And then sine 32 is equal to x over 2.5 because sine is opposite over hypotenuse. And that means that x is equal to 2.5 sine 32. So y is equal to 2.12 meters once you plug into your calculator, and x is equal to 1.32 meters. Now I'm gonna make this color coded depending on which one goes with which. So the y goes with the thrust and the x goes with the weight because of the way it's set up. Since the weight is pointing down and the x is horizontal, those are the two that you want to multiply. And since the t is horizontal and the y is up and down, they're perpendicular, so those are the two that you want to multiply. So now you gotta find the torque by multiplying negative 10,200 newtons. Give me a second while I make this all pretty. Okay, so multiply negative 62,300 times 2.12 because do you see how the y is perpendicular to the thrust? You get that answer. Negative. The answer is negative. And now you multiply negative 10,200 newtons times 1.32 because the W is perpendicular to the x distance when the x distance is 1.32, and you get that answer. And now, yep, that's the answer basically. Alright, one more problem guys, come on. So a square 0.4 meters on each side is mounted so that it can rotate about an axis that passes through the center of the square. The axis is perpendicular to the plane of the square. A force of 15 newtons lies in this plane and is applied to the square. What is the magnitude and the maximum torque that such a force can produce? Alright, I'm going to draw you a square. Each side is 0.4 meters. That little dot in the middle is the axis of rotation. Okay? If you were to divide 0.4 by 2, you get 0.2 and 0.2. They give you the force, which is 15. You know the radius, which is 0.2. Your torque is F times R, or 15 times 0.2. Your answer, in the end, is 3 Newton meters. Alright, so that sums up torque. If you guys are completely confused and didn't understand anything I said, I am sorry. This is the best that I can do. If anything, just rewatch the video. You guys are smart enough to get it if you're an AP.